Under the consequences of the Riemann-Roch Theorem, we can also state what is called Clifford Theorem. Clifford's Theorem. So far for the dimension of the Riemann-Roch spaces, we have observed that if the degree is negative, it is trivial. The Riemann-Roch space is trivial and its dimension is 0. And we have also observed that as a consequence of the Riemann-Roch theorem, if degree is sufficiently large, depending on the genus, then we can compute the exact dimension. And this theorem indeed explains what happens if the degree is between 0 and 2g minus 2. And in this case, it tells us, even though we can say the exact dimension, at least instead of having an upper bound as degree plus 1, we can also bound it above plus 1 plus half of the degree. And instead of giving its proof, actually here I want to mention about how we can use it. I mean, instead of telling how we can conclude about the dimension, I want to point out how we can use it in some questions. And for this purpose, I want to give the partial solution of the exercises 1.9. And in these exercises, we suppose that we are given a function field of genus G, and we want to show the four statements. I mean, the followings are the equivalent to each other. So that means genus 0. If the genus 0, then we will see that the existence of a divisor which has degree 2 and dimension 3. And next we will see that if we have a degree 2 divisor which has dimension 3, obviously we can say the existence of a divisor whose degree is bigger than or equal to 1. Obviously 2 is always bigger than 1, and its dimension is strictly bigger than degree A. And of course, by the assumption, if we want to show that B implies C, this also satisfies this inequality, its dimension and the degree. And finally, we will see that C implies D. That means the existence of a degree, the existence of such a divisor that satisfies these properties also gives us the existence of a degree, existence of a divisor whose degree is bigger than or equal to 1. And indeed, its dimension is exactly its degree plus 1. And finally, we will see that D implies C, and we will complete equivalence. And first, let me show that A implies C. So that means we suppose that the genus is 0. And if genus is 0, we will see the existence of such a divisor. And to see that, first, in a given algebraic function field of genus G, by the Riemann-Roch theorem, we know the existence of a spatial divisor, which is called canonical divisor. And let me consider a canonical divisor. And by the canonical divisor, what we want to mean that actually this is a divisor whose degree is 2g minus 2, and in this case, by the assumption, its degree will be minus 2, and its dimension is 0. And now, if we set, or if you consider its minus, and if we denote it by A, we can easily see that the degree of A is minus times minus 2. This is 2, and since the degree is bigger than or equal to 2g minus 1, by the assumption genus is 0, we know that its dimension is equal to degree A, its degree plus 1 minus G. In this case, it's going to be 3. And it shows the existence of such a divisor. And as I mentioned before, B implies C is trivial. To see that C implies D, so if we suppose that there exists a divisor that satisfies its dimension and its degree satisfies these inequalities, then indeed we want to see that its dimension is exactly equal to its degree plus 1. And to see that indeed we have no information about the genus, so this is why we distinguish the two cases. And in the first case, we suppose that its degree is bigger than or equal to 2g minus 1. Then, as a consequence of the Riemann-Roch theorem, we know that its dimension is exactly its degree plus 1 minus g. And by the assumption, so degree A is bigger than or equal to 1, and L of A is strictly bigger than or equal to degree A. This shows us indeed genus is strictly less than 1. On the other hand, we know that the invariant genus is always positive, and this shows us indeed genus is 0 and dimension of A is exactly degree A plus 1. And in the second case, we want to observe what happens if the degree is bigger than or equal to, less than or equal to 2g minus 2. And in this case, we can apply Clifford's theorem, which basically says the dimension is less than or equal to 1 plus the half of the degree. On the other hand, by the assumption in C, we know that its dimension is strictly bigger than its degree. And regarding these inequalities, in that we see that degree A is strictly less than 1 plus its half. Then degree A is strictly less than 2. But on the other hand, again, by the assumption, we suppose that degree is bigger than or equal to 1. This shows us indeed degree A is indeed 1. But if degree A is 1, so if degree A is 1, this means that the dimension will be strictly bigger than 1 and 1 plus half. But this is not possible, right? Because the dimension should be an integer, and if it is not equal to 1, it should be equal to 2, but 2 is not bigger than or equal to 3 over 3. 3 over 2, and this gives us contradiction. So that means this cannot be the case. And we show the desired equality between the dimension and its degree. And finally, to see that if there exists a divisor whose degree is bigger than or equal to 1 and its dimension is exactly degree A plus 1, we want to conclude that the genus of the function field is 0. Like in the previous step, again we distinguish it in two cases. And first we suppose that the degree is large enough. Then by the Riemann-Roch theorem, we know that the dimension of A is degree plus 1 minus g. But by the assumption, we also know that the dimension is exactly equal to degree plus 1, and this forces indeed genus is 0. And in the second case, if we suppose that degree is not large enough, again by the Clifford theorem, we can see that its dimension varies between 1 and 1 plus half of the degree. And by the assumption, if we plug in degree A plus 1 in L of A, thanks to these two inequalities, we can observe that indeed half of the degree A is less than or equal to 0, and indeed this shows us degree is negative. Cannot be positive, but this contradicts our assumption because we suppose that degree A is at least 1. So that means that cannot be the case, and this shows us genus is 0. So this is all what I want to say about the Riemann-Roch theorem and about its consequences. Of course, we will often need to use some statements and some consequences. But particularly next week, we will consider some characterizations of the function fields, like again, we briefly review the rational function fields, and we will introduce elliptic and hyperelliptic function fields, and we try to see what we can conclude about these two structures by using the language of the algebraic function field. So see you next week. Bye-bye.